Hello everyone, this is our project on modes of heat transfer. So we will discuss conduction, convection, radiation part, which are the way of transporting the heat. So this is our team members. So what is heat transfer? So basically heat transfer actually is an interaction between an object and its surrounding. So whenever there is a temperature gradient that is created between an object and its surrounding, so there is a heat transfer that occurs. Okay, so there are basically three modes in which it is occurred: conduction, convection, and radiation. So the first of all we are going to discuss is conduction. So it is a heat transfer through direct contact. What does it mean? We will discuss. So here is our conduction part. So basically the internal energy of the microscopic particles is converted into a different form of energy which is transferred from one place to another. That is our heat. Why this is happened? This happened because of temperature gradient that is created. So let's say we are heating a particular region of a object. So at that part the region gets hotter, and hence the other part will be cooler. So this will create a temperature gradient, and hence the heat will flow. So what happens on the microscopic level is that the region which is in direct contact of that heat gets more vibrated, they more get excited, and this excitement create their vibration, and hence in this way they transfer that vibration to other particle to their neighboring one, and in this way it is get transferred. So this is Fourier's law of conduction, which governs what is the rate of heat transfer through an object. So we have Q, and it is equal to Ka T hot minus T cold divided by L. So what is here K? K is basically thermal conductivity of material. So it depends on the material. Different material have different characteristic with different characteristic of K with respect to temperature. For example, like in our case of metals, this conductivity decreases with increase in temperature, and for our gases and fluids this increases. Okay, so this is Fourier's law of conduction. Now there are steady state conduction and unsteady state conduction. So what happens in steady state conduction, that after when we start heating the object, the temperature rises at a particular location, the object at that part absorbs some heat and releases some heat to other part, and in this particular case the temperature rises with time, and after a particular time the equilibrium is stored. So what happens then? Steady state is reached. Whatever amount of heat we are getting from the external medium, the same amount of heat will be delivered by the object to its surrounding or any other thing. So basically the temperature at a particular point doesn't change with time when the object reaches the steady state. The heat, it doesn't store any kind of heat. Rate of heat in is equal to rate of heat out. Time dependence, so basically it occurs after a very long time. And now we have a convection part.
Now, moving on to convection. It is the transfer of heat through fluids, that is, liquids or gases, by the actual motion of the fluid. When a fluid is heated, it expands, becomes less dense, and rises. Cooler, denser fluid then sinks, setting up a continuous circulation called a convection current. In this image, we can see this process clearly. Warm fluid rising from the heat source and cooler fluid sinking down to replace it. The principle behind this is buoyancy-driven motion. Heat causes density differences in the fluid which create these circulating currents that carry energy throughout. Now, there are two types of convection, natural and forced. In natural convection, the movement happens on its own due to temperature-induced density differences, while in forced convection, an external force like a fan or a pump moves the fluid. Hot air rising from a heater is an example of natural convection, and an air conditioner cooling a room is an example of forced convection. Newton's law of cooling. Newton's law of cooling describes how quickly heat is lost by convection. It states that the rate of heat transfer is proportional to the surface area and the temperature difference between the surface and the fluid. The image here shows how a hot object cools faster when the temperature difference with its surroundings is higher, a direct application of the Newton's law. Now moving to the third mode, radiation. Radiation is the transfer of heat through electromagnetic waves like infrared or visible light. Unlike conduction or convection, radiation requires no medium. It can occur even through a vacuum. The image here shows the sun transferring heat to the earth through empty space. The principle is that all bodies have above absolute zero temperature emit radiation, and the amount depends on their temperature and surface properties. Stephen Boltzmann law. Stephen Boltzmann law quantifies radiative heat transfer. It says that the radiated energy is proportional to the fourth power of the absolute temperature. Absorptivity, reflectivity, and transmissivity. When radiation strikes a surface, a part of it is partially absorbed, partially reflected, and partially transmitted. These are then defined by absorptivity, reflectivity, and transmissivity. So for most of the solid that we will encounter, transmission is almost zero. So absorption and reflection dominates. The image here shows an incident ray dividing into three parts: absorbed, reflected, and transmitted. Now, these equations are derived from energy conservation. P plus alpha plus tau equal to 1, where P is the total reflectivity, alpha is the total absorptivity, and tau is the total transmissivity. So, as I said, most of the solids that we encountered in engineering practice are opaque. So, due to that, transmittivity becomes 0, and equation becomes P plus alpha equal to 1. So, lastly, to summarize, conduction transfers heat by molecular contact, convection by fluid motion, and radiation by electromagnetic waves. All of the three work together in nature and engineering, from cooking and weather patterns to spacecraft designs. Thank you.